Alright, so today we are going to work on solving trig equations using multiple trig functions. What that really means, it's kind of a blend between, proofs and solving like we've been doing the last couple of days. And basically, it would be where you have two different trig functions within an equation, and you'll have to use some of the identities and some of the ideas that we've done with proofs in order to get it to all be the same function. So from there you could factor, or you could solve it like what we've been doing the last couple of days. So take a second, pause, write that down if you want, and then what we're going to do is I'm going to work out this example here. I'm moving around the screen. I'm going to work that out as we go through the steps so you can kind of get an idea of what the steps are actually referring to. So first thing you want to do is you want to see if there's any functions or identities that you could substitute. Because once again, we need these to match. Because I can't add sine and cosecant at the moment. So what I know is that cosecant would equal 1 over the sine of theta. So I'm going to try to replace, using identities, get things to be common terms. So that's what I'm saying here, like terms or something that we could factor. If not, you could square both sides to see if you can get a Pythagorean identity. That's not the ideal situation, because what happens when you square both sides, as you'll see when we do one, you have to check for extraneous solutions. And if you don't remember from Algebra 2 what that means, basically what happens is since we're squaring everything, squaring cancels, turns everything positive, gets rid of all the negatives. And so when you do that in an equation, you just start squaring everything. Then some of your answers may or may not work because they were all turned positive and then solved. And so when you actually go back and you check your answers with the original equations, some of those original negatives might have disappeared, and therefore the solution doesn't actually work. In this case, so here we have all common terms. So what I'm going to do is we don't want to solve for a function in the bottom of a fraction. I want to multiply everything by sign. So I'm going to multiply it to this, to that, and to the negative 2, because I want to get rid of the sign in the denominator. So then we have the sine of theta squared plus 1 equals negative 2 sine. And so from here, now you can see this is just like what we were working on the last couple days. So if we reorder it, we add the 2 sine to both sides, as it is a quadratic. So you can either factor or you can use a quadratic equation. But because of that, remember, you have to get it equal to 0. So add it to both sides. So we end up with a sine squared theta plus 2 sine of theta plus 1 equals 0. So when this factors, remember, if you're not the best at seeing how to factor it, once you have it all at common terms, replace all the terms with a variable. It has to be the same variable. But in this case, replace them with x's. So then this becomes x plus 1 times x plus 1. So that's x plus 1, that whole thing squared. So when you solve, we take the square root. So you get x plus 1 equals 0. So x would equal negative 1, which means that sine of theta equals negative 1, which hopefully you remember. Therefore, theta would equal 270. So that's what we're doing here. Alright, so let's take a look at this one. In this case, this is the exact example I just did on the other page. Keep in mind, on the test, it will have this here, which is solve on the interval between 0 and 360. What that means, more or less, it's what we've been doing. Finding the theta, just making sure it's in between those numbers. The key thing to take away from this is that this is between 0 and 360, which means theta should be a degree. So make sure your answer is in degrees here. If it was like 0 to 2 pi, then your answer is a radian. Alright, so now we get into more complicated angle measures. Here, first thing we want to do is we want to see if we can find an identity that we could get rid of this 2 with, because this is a regular theta, that's a 2 theta. We don't want them to be different, we want them to be the same. So hopefully you recall that sine of 2 theta equals 2 times the sine of theta times the cosine theta. And what we're going to do here, we're going to get them both to the same side because we're trying to factor, which means I'm subtracting sine to both sides. Alright, so subtract sine to both sides. Now we want to see, is there a common factor between that and a common factor between that? There is. It's a sine. So we take out a sine of theta, and what you're left with is 2 cosine of theta minus 1 equals 0. Now, a lot of people will ask, well, how do you know what to do, or how do you know that that's right? And what I'm looking for is once you have it factored, it means 2 things being multiplied. This factor has to have all the same trig function. This factor has to have all the same type of trig function. So here this factor only has a sine. This factor only has a cosine. So that means we did it right. If you had a mix of like sines and cosines within the same factor, then something's not right, and you should go back and relook at it. And since this is right, we set both equal to 0. So sine of theta will equal 0. So that's coming from here. This guy, you get 2 cosine of theta minus 1 equals 0. So we're solving this one. That's the easy one. What makes sine equal 0? Hopefully, that's a unit circle question. You remember that it's 0 and 180 degrees. So that's our first set of solutions. The second set now, well, I'll double check. Okay, right interval, 0 to 180. That's good. So this one gets the cosine by itself, which means we're adding 1 and then dividing everything by 2. So you get cosine theta equals 1/2. This would be a type of problem you could see on the no calculator part, because both of these factors, this one and that, they're both exact values. So what makes cosine equal 1/2? You go to the unit circle and look. Theta would need to equal 60 degrees and 300 degrees. And like I said, those are just coming from the unit circle looking on the x coordinates in quadrants 1 and quadrant 4. Oh boy. That one, this is one of the ones where you look at it, there is no there is no substitution that we can do to help ourselves here. So we're going to have to square both sides and work it out. So what I'm going to do, I'm going to work it out, and so you can kind of just follow along, and then we'll talk about how to check your answers and stuff in a second. So at this point, we got to plug those answers back in to the original equation. And so, key thing, make sure it's in the original equation. So it's in this guy before it's squared or any of that stuff. I mean, it has to go into that. And so if you're looking at these solutions, we're just going to go through this real quick because I want to get to the next one. But here, 90. Sine of 90 is 1. Cosine of 90, 0. 1 plus 0 is 1. So that one works. That's a good answer. If I plug in 270, sine of 270 is negative 1, plus cosine of 270 is 0. Negative 1 and 0 does not equal 1, so that does not work. 0, when you plug it in, 0 will work. That one, 180 will make this equal negative 1, so it doesn't work. So you end up with your two actual answers of 90 and 0. Alright. On this guy, what you need to do, you're going to have to get them all in the same terms, so we're looking at substitution. I'm substituting that one to get 4 and 1 minus cosine squared of theta plus 4 cosine of theta minus 5 equals 0. So I want to work this one out. So pause the video real quick because I'm just going to show the answer because I'm running out of time. Here's the work for the last problem. So hopefully you tried it on your own. Get something similar. If not, ask about it in class tomorrow. Here's the homework. Hope it makes sense. We'll see you guys later.